Hello friends, how are you all today? Have you ever wondered what operating system is and how it is going to work? It's coming up right now. I'm Prashant, a technical trainer and freelancer from Dharani Academy of Technical Education, Bengaluru. Let's start with the concepts of operating systems.
Right. So we were looking at the reason why we need what is called as a page replacement. Okay. So when everything is filled, and we don't have any other option in multi-programming system, right? We have to use what is called as the page replacement, right? So what is the approach used in page replacement that we are going to discuss today first? Okay, so let's start with the concept that we are going to find no frame is available. Okay, uh, so let's write with that. So if no free frame, right, this implies we find the one that is not currently being used, right? So when you are not able to find a free frame, then the next step is that you find one such free page in the memory that is not currently being used. Okay, it has been loaded, but definitely there will be a chance that it's not being used. Most of them will be being used, but try to find out one such frame which is not currently being used. Okay, and what we do, uh, and we try to free that. Okay, and free it. When we see, the idea is that we can free a frame by writing its content into the swap space in the memory and changing the page table accordingly, just to indicate that the page is no longer present in the memory, right? So that's the idea now. So we'll see the steps, right? Which exact steps needs to be followed to have the page replacement. But now we are looking at its basics, right? How can you free a frame, right? So we can write one can free a frame by writing the contents to the swap space of the memory. So we know that there is this swap space, right? And we try to write the contents of the page to that location, to the swap space. And after that, what we do, you need to change the address. Okay, and changing the page table we try to change the page table to indicate that the page is no longer in the memory. It was loaded so far. Now you say that it's not available and it's no longer valid, and it is not going to be present in the memory. Okay, so now we just have to uh, understand that how this can be done. So for which reason we'll look at a diagram. Okay, next we'll write a diagram to make sure that how this is going to be done. All right. Okay, now fine. So first let's try to write the page table, the original contents of a page table. And in a page table we definitely have the space that is allocated for valid or invalid bit. Okay, so let's write that here, and then let us write some of the pages valid and invalid will write. So let's say, okay, let's consider these things. So first part is a frame, second part is valid invalid. Okay, so I'll write say something which is 0, maybe this is I, indicating that this is invalid. Then I'll write something called F, which is say valid. Okay, now what exactly is going to happen in the physical memory, right, when we look for a page replacement? Okay, so let's write that part now. So this is the physical memory, and in physical memory, let's consider, so it says that F is valid. So at a specific location, say F, right, is the one which is being replaced now, because F is actually loaded, right, but it is not being used. So I will call that location as a victim, indicating that this is the one which is going to be swapped out. So we'll swap something out and we'll put some required data into this position. All right, so that we can show in the yeah, in the physical memory, so in terms of a cell, right? So let's copy that. So we know that it is located over here. All right. All right, so this is the disk, and in this disk, let's say, so the victim needs to be swapped out first. So what do you mean by swapped out? This data is going to be moved out to some other location in the swap memory. So that will be the step number 1, right? So this one refers to swap out the victim. Okay, then we are actually looking for the memory, right, and we didn't get the memory. So what we do, we swap in the required page. This will come back, but this happens as a different step. What happens here is uh, now as you move this, right, so what happens is step number 2. I'll write a step number 2 here first. So okay, let me write the step number 2 here. That is, you change the validity, valid or invalid is there, right, that particular bit. So change to I can say invalid. This is the step number 2. You swap out this, and when you move this out of the memory, we know that it's no more valid. And when the memory is not valid, I have to update that on my table first. So that's why I make it invalid. Then I'll come to the step number 3. All right, the step number 3, it's swap in the desired page. So you can see that this is the desired page which we are trying to bring it into the memory. All right, so now that's done. Once it is done, now we go for step number 4. Okay, so update the page table. we are going to update the page table as per the requirement. Okay, so now whatever was the required data, it is actually present in the position F, so you can update the table as required. Okay, so this is the physical memory. That's the physical memory. So this is how these are the different steps that we have to follow whenever we don't find any free space available, and we find that some of the pages which is loaded in the memory are not currently being used. In such case, we can definitely do a swapping operation. Okay, all right, so let's write the steps to be followed. So what we do initially is that, so okay, we start after find the exact location of the desired page on the disk. Locate where is it present. Okay, then the next step is find a free frame. So finding the free frame, right? Uh, how can you use it, right? So free frame is available means you can use it. So let's write in as a sub part. Okay, so that is if a free frame is available, right? If it is available, this implies, right, you can simply use it. I check whether there's a free frame. Yes, it is available, you can use it. Okay, if there is no free frame, use a page replacement algorithm to select what is called as a victim frame. We need to select one victim frame. So how to identify the victim frame? We use the page replacement algorithms. Okay, so if no free frame is available, then what we have to do, right, we have to use a page replacement algorithm to select, to identify what is called as a victim frame. You will identify a victim frame, right? Now, right, in order to make that victim frame as a free frame, we need to write the victim frame to the disk, change the page and the frame tables according to the operation we carry out, so that it becomes a free frame. Okay, right. So next we write the contents of the identified victim frame to the disk. That's what we marked as disk swap out. So you swap it out to the disk. Okay, so frame to the disk, comma, I need to change the contents, the address. So this is change the page and the frame tables accordingly. So once either of these three, A, B or C, is completed, we know that we have a free frame with us. Okay, so that will be the second step in this page replacement concept. Then in the third step, what we do here is we first read the desired page because there's a free frame available. Now I need to read the page and replace it on the page table as well. Okay, so first we read which one? Read the desired page. This is what I want to overwrite there. Okay, this into newly freed frame. Check that what is the content, and you simply need to read that into that frame. Then change the page or the frame table. Okay, once this is done, now you know that the process which actually had requested some memory and that was not present and the process is on hold, you can actually continue or the restart the process. So next step is continue, or in some cases you may have to restart that process. So restart the process. Okay, so that is how it gets done, right? As a result of this, what we have here is right, this whole process is called as a page replacement, where some pages which was requested, which was not present, now we are trying to uh, perform the page replacement and we have the required page with us. Okay, all right, so that's the page replacement technique. Normally whatever we use to perform a page replacement, in some of the author textbooks they call it as a frame allocation algorithm. So just remember, I'll write a name. So it's also called as frame replacement algorithm. All right, now let's go to the concept. We need to check a few page replacement algorithms now. So the first one which we are going to study is called as FIFO, first in first out page replacement. Okay, so one of the very simple algorithm that found some of the OS use when they want to perform the page replacement. Okay, so what happens here in FIFO replacement algorithm, this basically associates with each page the time when the page was brought into the memory, right? So we try to associate a time with that page. So whenever the page comes into the memory, you associate a time with that. Okay, this was bought at at say 6 hours 30 minutes and 40 seconds. Next, one more page comes, 6 hour, right? 50 minutes and some time needs to be associated with that first. It's not exact, it may not be the exact time of arrival, but we call it time. You can even allocate numbers. This is 0th frame, this is first frame, this is second frame, third frame, and so on. You can assume that. All right, so what it does, we'll write first this algorithm associates with each page the time is being associated with each page when that particular page was brought into the memory. like you are going to have a timestamp on each of the uh, page that comes into the memory. So now whenever a page must be replaced, right, simply you will choose the oldest that is oldest page that is present. Whoever came first, you always try to replace that particular frame. Okay, so that's why the name is first in first out. So when a page must be replaced, what do we do? The oldest page is chosen. You choose that. Okay, so normally we create a FIFO queue to hold all the pages in the memory. That's all. So it's simply like a queue. We replace the page at the head of the queue when a page is brought into the memory, right? We insert it at the tail of the queue. So, right? Very simple process. Okay, right. So we'll write that point here. Okay, if a FIFO queue is created to hold the pages loaded to the memory. Whichever page is loaded, it enters into a FIFO queue. Whoever came first can go out first. So what we do, we replace the page at the head of the queue. We replace the page at the head of queue. And where you are going to replace it, so a page which comes in, right, will go to the tail of the queue. So we can write when a page is brought into the memory, whenever you are bringing it into the memory, we always insert it to the tail of the queue. Okay, all right. Now next let's go to the one example using which we can demonstrate what exactly is happening here, right? uh, let's consider a string and let's assume that our three frames are empty. So three frames are empty. First three references, let's try to give a reference to them. Okay, let's try to write one diagram here, right? Okay, so that is initially this is the case. Let's say we have sorry. Okay, let me write three frames here. 2 and 3. Okay, so we'll try to write the reference strings at the top maybe. So I'll write 7 0 1, right? So 7 is the maybe the last one, then restarted from 0 1 2 etc. Okay, so we call it as a reference string. Let's assume that this is going to cause page faults and they are brought into these empty frames. Whatever comes in will come to these frames. So reference string, you can see, I'll fill the reference strings later. But what happens initially, my frame gets filled with 7. So this is my reference string. Okay, so has nothing to do with this. Okay, I'll slightly move it to a different location so that we don't get confused. Okay, so what I'm writing here is some frame number. Okay, so those frames are causing page fault. Okay, so let me move this slightly below. Okay, let's say this is here, and let us assume that the frames which cause the page error, page fault, are as follows. So first I'll write here the reference string, maybe initially 701. So we have these uh, strings coming, and each of this, so maybe this is the instruction number. That instruction resulted in a page fault. Whatever data we require to execute that particular instruction is not available in the page file. So it means it throws an error called page fault. So as soon as it is not available, you will put it into the queue, right? So 7 is in the queue. Then I know that next number will come to the next position, that is 0. And as soon as the 1 will also throw up an error, because when 1 is not executed, you will give a chance to next. That's also not getting executed, you will give a chance to next. Okay, so that's how we are giving chances to all the instructions one by one, and whichever is not getting executed, you are going to put it on a queue. Okay, so that's what is happening. So 701 is there, so 7, then 0, then 1. Now you see, if at all there is another another number comes, reference string comes, and if that is not getting executed, and if you want to put that into which location, if I want to put it into my what you call queue, right, then definitely I'm supposed to put that into a location where the oldest string exists. So what happens? So these are reference strings are written over there, and what I'm writing now below is it's a reference to the page frames. So I'll simply write the page frames get sorry get updated as follows. So which is the oldest one now? The oldest one is 7. So when I write another frame over here, so how it gets replaced? You replace the oldest one first. Which is the oldest one? That is 7. So 2 replaces that. 2, 0, 1. Okay. Now you see, let's assume the next number is 3. Okay. Now what I expect? I expect the oldest one to be replaced. In this case, I am assuming every string, reference string that comes is going to generate a error, page fault. In such case, how the frames are getting updated, we'll see. So 2 is not the oldest one. Right now the oldest one is 0. So 3 is going to be replacing that. Then 1 as it is. Okay, right? Now I say, okay, 0 came once again. So which one you are going to replace now? You will replace the last position, because 1 is the oldest as of now. So oldest one will get replaced always, first in first out. So 2, 3, and now the 0 comes over here. Okay, and so on. You can keep replacing the strings, right, that comes up, and you can, right, always try to replace. Now I have a question, like what if a string comes now which is once again 2? You don't have to replace because 2 is already there. which is present already, right? You don't have to do anything. So 2, once again you can write a 3, maybe. It's not going to replace anything because that particular number is already present in the queue, which means I don't have to replace. Okay, in this fashion it proceeds further, right? You can keep generating. I'll show one more, maybe I'll put a 1 here. So now this means, right, you have to update because 1 is not there in the queue. 1 was there earlier and it has been replaced by some other number. So now the oldest one is 2, so that gets replaced. 1, then 3 and 0. Okay, if something which is already present in the queue comes up, means you don't have to replace. So just remember this, using this technique we are updating the pages, and this is called as the FIFO technique. Okay, all right, that's the first technique, straightforward. And with after this example, now we'll go to the second algorithm for page replacement, and this algorithm is called as LRU page replacement. LRU page replacement algorithm. This is basically referred to as the least recently used. LRU stands for the least recently used. Okay, fine. Now how this works? This basically, this LRU always tries to associate with each page the time of the page that it's being used for the last time. Okay, so now you see you are going to mark each page with the time when the page was used for the last time. So this algorithm associates with each page the time of that page's last use, previously when it was used. Okay, when a page must be replaced, the LRU is going to choose the page that has not been used for the longest period of time. This is also pretty straightforward. You just have to check which is oldest. Okay, so when a page must be replaced, whenever this must be replaced, the LRU chooses that page which has not been used for the longest period of time. Longest period of time. So now let's look at the example, how this is going to work. Let us consider the similar example now, and let's write the reference string. Let me write the similar reference string, and maybe I have 701. Initially I'm starting with that. So first place, I'm assuming the frames are completely free. Okay, so in this condition, so when the 7 comes up, you are going to fill this. Then the next string comes. Okay, 7 0. Then the next string comes. We have this completely filled now, 7 0 1. So now what exactly happens, right? As and when it is coming, you are using it. So 7 has been used, then 0 is coming, 0 is being used, then 1 comes, 1 is used. Now I understand that the one which I used most of the time is 7. Okay, then let us assume that 0 was used in the middle once again. Okay, for which I'll write something like this, 7 0 1. Let me write my next number. 2 comes. So when 2 comes, right, what happens? When 2 comes here, which is the oldest one and that has not been used, is 7. So I have to replace the 7 now. So 2 0 1. Now I assume 0 comes. So that 0, you don't have to worry, it's already present and you use it. So now which is not used for long time is 1. Okay, so that's why whichever comes next, I'm going to replace the 1. So let me assume that we got a 3. Okay, so when this comes, now I understand that 0 just now used. Okay, so 2 is not the oldest, so 2 is also fine. 0 is the most recently used one, it is not going to be replaced. 3 is the one which replaces 1 now. Okay, all right, so now this comes. Then let me say 0 comes once again, just to show that the most recent one I want to replace. So 0 means 0 is already there, so 0 I'm using this. So whatever comes next, if at all 4 comes, okay, so that means I'm actually going to replace the 2. Okay, all right, so now because of that I'm replacing the 2. 2 is the most oldest and not being used for the long time, so 4 0 3. Now if 2 comes, right, you know that 0 has been used, 4 is the newest one, so which one to be replaced? Now the 3 gets replaced. Okay, oh, sorry. So in this case 4 0 2 and so on. Now this is quite different than what we saw in the previous example, right? So previously it was first in first out. You were not going to look at which position it is and how long it is present and whether it has been used or not, we don't check. But in this case, it's least recently used one will get replaced. Okay, it doesn't matter if you are using something for more times, that will remain in the queue, because that it actually saves a lot of time for the processor because it's already present. Okay, so that's how the LRU algorithm is going to work. Then we have a different technique which is called as, let's go to the next one. So this is the example for LRU. Then we have a different one that is called as page buffering algorithms. So in this case, the page buffering algorithm, there is no step to be followed, because steps are not what we are going to look here. We just look what is a page buffering algorithm. Okay, normally whatever procedure that have been used so far, so specific page replacement will be done, right? Systems commonly keep something like a pool of free frames. We already have seen that yesterday. When a page fault occurs, victim page is always chosen according to the algorithm. Right. Now, the desired page is read into the free frame from the pool, right? Before the victim is written out. So this allows the process to restart as soon as possible without waiting for the victim to be written. So in the previous case, we just have seen that you read something, you replace the victim page and you overwrite them so that you don't have to wait. Okay, but now what is a page buffering algorithm? Page buffering is the same thing, right? So we try to give an expansion to the idea which we have studied so that you maintain a list of modified pages. Whichever page that has been modified, you try to keep a complete list of that. Okay, so here we directly start from that point. So just to fast up the process of the restarting process. Okay, to uh, allow a process to restart quickly as possible after a page fault. When a page fault occurs, it has to do some steps, it has to follow the steps, and then it needs to restart. So just to allow a process to restart as quickly as possible without waiting, okay, what you do, we always try to we maintain a list of the modified pages. Whichever page has been modified, you keep trace of that. So why? It is because whenever a paging device is idle, the modified page will be selected and you can write that to the disk. Okay, so that you can free up that space. Anyway, I know that the modified page is present over my virtual memory, right? That location or that page may be required for other processes. Okay, so how do you fast the things up? You can you can write this page onto the disk whenever the paging device is idle. So whenever the paging device is idle, a modified we can say modified page is selected. It is selected, and whichever is selected, it is written to the disk. You will write it to the disk, right? So its modified bit will be reset. So this scheme increases the probability that a page will be clean whenever it is selected for replacement, and you don't have to write it out. So it's already written, correct? So whenever we looked at the page replacement algorithm, we understood that whenever one frame which is filled, right, you try to access that you see that it's not a free frame. You have to make the frame free by writing it onto the disk. But now, just now you understood that here we already write the particular page onto the disk and it is readily available. You don't have to wait for writing a process. Directly you can put your data over here and you can use it. Okay, so because of that, this particular algorithm helps up speeding up the process. So this algorithm, page buffering algorithms, they are going to help you in increasing the speed of writing the process. Okay, so this particular scheme, in the sense whatever you did now, this increases the probability, increases the probability that a page will be clean whenever it gets selected for the replacement, and because of this is already being written, now it's not necessary to be written out, so that I can write and will not be written out, so you save some time. All right, so that's one type of the page buffering technique, and there can be another modification. This is to keep a pool of free frames, but you will remember which page was in each frame. Okay, there is a free there will be a pool of free frames, but there will be a memory associated with that. Okay, to remember which page was in each of these frames, older contents will be remembered. So the frame contents are not modified when the frame is written to the disk. Okay, the old page can be reused directly from the pool. If at all you need a older value to be taken back into the memory, you see that normally it will be, you have to find out where is it present on the disk, and then you put the data back to the disk. But now you see that its older value will be retained. Okay, if the older value is retained, advantage is that you have a pool, and pool already contains some data, right? Simply bring it back. Okay, so that's another added point to the page buffering algorithm. Okay, so to keep the technique, it continues here with the same page buffering algorithm. You also have to keep a pool of free frames. Okay, this is as usual, we know that there will be a pool of free frames, but what is the added part? So that is, but to remember which page was present in each frame. So when we do this, what's the advantage? Advantage is something like, frame contents are not modified when the frame is written to the disk, so the old page can be reused directly from the free frame pool. All right, so this implies the old page can be directly reused. You can reuse it whenever you want. Okay, reused from the pool itself, from the pool. If it is needed before the frame is used. So frame is already there in the free pool. If somebody wants the free frame itself, then we will clear the data and we'll use it. But if the same data needs to be used, That's also possible. You see, you speed up the things, right? Whenever the reusing concept comes, right, we can use this. So specifically, the Unix OS is going to use such page buffering algorithms. So as an example, you can please note that uh, Unix environment will use these kind of the free pools, right? You put a frame to the free pool, but you will never clear that. Okay, contents will be retained only when you don't have any other option. You will clear the contents. Otherwise, the content will be kept as it is, thinking that okay, these contents might be required at a later stage. All right, so that's the example of the what is called as the page replacement. Okay, then we go to another concept that is called as the frame allocation. Frame frame allocation, right? So see, the frames are supposed to be allocated to processes, right? In the sense, in what way the frames are allocated to several processes that expect frames to be given to allocated to them, in what order they are going to be allocated. Will it be a fixed amount of memory or will it be a variable thing? We are going to consider that. Okay, so for example, you can consider that there is a 128 KB memory available, right, which contains several pages and each page is 1 KB size. Okay, so just an example. So 128 KB I have, 1 KB is the size of every page. So I understand that totally 128 frames are possible, because one frame is 1 KB, totally 128 KB, out of which OS itself is a software which will require some memory to get stored. So let's assume that some 35 40 KB is gone. So when 35 KB is removed from 128, I have 93 frames left. Okay, now out of the 93 pages, how you are going to allocate the memory that is required by each and every other processes that's going to run. So this is what is the concept called as memory allocation. Okay, so this is the concept is about allocation of the available frames to various processes is called as frame allocation, right? How the OS is going to perform this, we'll see. All right, so the first one is let's say that the first technique is minimum number of frames. You try to allocate the minimum number of frames. Okay, write that minimum number of frames. So always try to allocate the least number of frames. You fix a least number, like okay, 5 frames I'll give. In the sense, I'll not allocate less than 5 frames to any of the process may request 3, you give 5, because the least possible number you fix it to 5. Okay, okay, so here you always try to allocate at least, it's a least possible case, that's why I call it as at least a minimum number of frames. You always allocate like this. Okay. Why you are going to allocate a least number of or the minimum number of frames, right? That actually this answer is directly related to the performance, right? Why it is performance? Because you are going to decide that the number of frames allocated to each process, if it is decreased, right, you know that the page fault rate will increase, right? Because whenever you keep it lesser than, as you keep reducing the number of frames allocated for every process request a page, and that page may not be present in your memory because you have allocated very less number of pages to that. Okay, so it's always good to allocate a fixed minimum number. Minimum number is fixed. You, whether you ask 4 or 5, we always allocate 10, something like that. You keep a fixed number. So why this is because, I'll write the next point, because as uh, the the number of frames allocated to each process decreases, right, the page fault rate increases. It will increase because most of the processes will not get a page in the memory because they have very less amount of space allocated to that. Okay, so this means, what is the indication of that? More page fault indicates, right, I told it directly depends on the performance, right? Process execution becomes slower. So I can write this implies slower process execution. Slower indicating that your performance is reduced, right? So in addition to this, we can understand one thing, that when a page fault occurs before execution of an instruction or before the execution gets complete, instruction must be restarted, right? We saw in the previous cases wherein not only you waste some time, you restart the whole process once again. So this means we must have enough frames to hold the different pages at any single instruction, can be using it as a reference. So I'll simply write, so this implies, what is the condition? We must have enough frames. You should have enough number of frames to hold all the different pages. So what is the overall idea? You always try to keep a fixed minimum number, right? This minimum number should be, right, chosen properly. Like, you don't keep it like 1, 2, or simply say 5, right? That may not be sufficient. Out of all the processes that exist, right, minimum page may be 10. So you keep 10 for all of them at least. Okay, which always tries to reduce the number of page faults that occur, right? It should be sufficiently low such that you can handle them, and most of the time is not getting wasted. Okay, so the first technique is that it is called as minimum number of frames. Always you try to get a minimum number properly selected so that it handles every page fault that comes efficiently, effectively, without affecting the performance of the system.